All of us who have worked with individuals with aphasia, it's easy for us to spot a person with non-fluency. These are usually individuals who have great difficulty speaking, and it looks like such a great effort for them to get the words out. However, if I ask you to give me a brief one-sentence objective description about who is non-fluent, you would probably find that very hard. And the reason is not because we don't have objective criteria for defining fluency. We do. There are measures such as words per minute, which is usually constrained between 100 and 175 in neurotypical individuals. And people have proposed such criteria to define non-fluency. Depending on whom you ask, they would tell you maybe less than 50 words per minute or 100 words per minute, or they might cluster different people as having different degrees of non-fluency with these measures. But the issue is that a lot more seems to go into perceiving someone as non-fluent rather than just a quantity of speech. So here I have put up the Western Aphasia Battery's revised criteria for fluency scoring system. And my goal is not at all to go through all of these categories. I've just highlighted here and there a bunch of criteria to show you that various aspects of speech production seem to matter for the judgment of fluency. For example, stereotypical speech, if somebody fluently keeps saying, I don't know, doesn't really count towards them being fluent. There is also the question of paraphasias, phonemic jargon, neologisms, the prosody of speech, and of course, the grammatical complexity of utterances all matter for judging someone as fluent or non-fluent. So this should already show you that it's pretty hard to come up with a very simple description for who is non-fluent. So then it's even harder to try to understand why someone becomes non-fluent. And this is why I think that despite so much research on the topic of non-fluency, we still don't have a good comprehensive picture about the origin of this phenomenon. So what I'm going to do today is to propose a slightly different approach, a psycholinguistic approach, by looking at the literature that have defined how we produce sentences, and go over various operations that are involved in sentence production, and basically argue that, at least theoretically speaking, a lesion to any part of the system that affects any of these operations should lead to non-fluent speech. I'm going to then briefly review evidence that have linked non-fluency to these various operations, and then propose a statistical approach that allows us to put all of this together in one big model and then test that model using a large database. So the model that I'm showing you is from Ferreira and Slevik 2007, but the spirit of the model is similar in other approaches to speech production. So the very first step in producing a sentence is generating a conceptual message. And in order to do this, you need to have a good comprehension system. For example, if you are in a conversation with someone and they ask you a question that you don't understand, obviously it is very hard to generate a fluent answer because you don't even have a coherent conceptual message to start from. And the relationship between comprehension and fluency has been the subject of many studies. And usually, at least traditionally, we think about this in a dichotomous fashion. We traditionally are used to mapping fluent aphasia to Wernicke's aphasia and non-fluent aphasia to Broca's aphasia. And again, we think of Wernicke's patients as having comprehension deficits, but Broca's patients as having relatively intact comprehension. And so with this tradition, if you think about it that way, then we would think that fluent aphasics are those with comprehension problems, but non-fluent aphasics should have no comprehension problems. And there is at least some evidence to question this assumption. For example, Schwartz, Safran, and Martin have shown that patients with non-fluent aphasia can have subtle but real difficulties in sentence comprehension. And the examples that they use is when thematic roles violate traditional conventional meaning. for example, their patients were fine in understanding a sentence such as the dog chases the cat, but they had trouble understanding the cat chases the dog. So what seems to be missing from the literature is a more nuanced study of the relationship between the degree of comprehension deficits and the magnitude of non-fluency. Moving from that, assuming that you have generated a conceptual message, now the next step in sentence production is two sets of parallel processes that have to be completed. Ferreira and Slevik call them content processing versus structure building. Roughly speaking, content processing maps onto what we think of as single word production. This encompasses lemma selection, and in models that have lexemes, selection of lexemes. Some models put some operations with morphological selection here, and there is, of course, phonological selection, phonetic encoding, and ultimately articulation. The relationship between single word production and fluency has also been studied in many, many bodies of research. And there is at least some evidence that the two might be linked. For example, there is evidence that lesion to certain parts of the brain, for example, arcuate fasciculus, produces both lexical retrieval difficulties and non-fluency. But obviously, this is not a causal relationship. There is also behavioral reports linking object and action naming deficits to non-fluent aphasia. But again, the relationship to fluency is not clear-cut because there are also studies that show similar deficits exist in fluent aphasia. And if you look at other literatures in which fluency is a main problem, for example, stuttering, you see a very similar debate. There are lexical retrieval deficits that are sometimes exclusively linked to non-fluency and sometimes not. And finally, when you look at structure building, you can contrast structure building with content processing in the sense that while content processing focuses on all the operations that are necessary for producing a single word, structure building, on the other hand, focuses on operations that link different words in the sentence. This is something like building a syntactic tree, or assigning thematic roles to the different parts of the sentence, or keeping the dependencies, for example, keeping track of whether you have produced a singular or a plural subject, and accordingly whether you need a singular or a plural verb. And the relationship between structure building, and so this is what we usually think of as syntactic production. And the relationship between this operation and fluency has also been the subject of a large body of literature. To begin with, syntactic complexity in a sentence seems to be predictive of how much people produce disfluencies. This has been shown in neurotypical adults, in children, and also in people who stutter. In aphasia, the same kind of dichotomy that exists in the relationship between comprehension and fluency seem to exist in the relationship between syntax and fluency. So we usually think of fluent versus non-fluent patients as grammatic versus agrammatic patients. And intuition tells us that there is this relationship. When you usually see a non-fluent patient, they have problems in producing grammatical sentences. But interestingly, when my colleague Yasmin and I were working on this project, and we surveyed the literature for a definite link between agrammatism and non-fluency, we couldn't find such a link. And the reason is because there are lots of studies that report morphosyntactic impairment in non-fluent aphasia, but there are also lots of studies that have reported similar problems in fluent aphasia. So although we all have this intuition that agrammatism and non-fluency go hand in hand, clear objective demonstration of this has been missing from the literature. And so again, here what is needed is a more nuanced study to see if really the magnitude of grammatical problems track the magnitude of non-fluency. And of course, apart from these core processes, you have other operations that matter for sentence production. For example, you have working memory operations that we now are pretty sure matter for producing fluent sentences. And the reason for this is, again, because of the structure building part of sentence production. You have to keep track of what has come before in order to be able to complete the sentence in a reasonable way. If you forgot what the subject of the sentence was, it's hard for you to produce a verb that agrees with that subject. In the same vein, there are monitoring processes, and some of the work from our own lab has shown that monitoring processes matter for all sorts of things in aphasia, and they also matter for fluency of speech. At least this has been shown in stuttering. But there is still the need for a lot more work on the relationship between working memory, monitoring, and fluency. So ideally, what we want is a model that accommodates all of these variables and can simultaneously look at the relationship and their influence on fluency. So note that the past literature has investigated the influence of these variables in isolation on fluency, but none of the studies that we could find have put all of these variables simultaneously in the same model. And this is important because a patient might differ in more than one variable. For example, you could have two groups that differ on comprehension and look at the effect of comprehension on fluency, but miss the fact that the same two groups may differ on other variables as well. So it's important to build a model that has all of these variables simultaneously in it. And if this is not complex enough, there is even more complexity in the sense that these variables are not independent of one another. For example, in order to produce a word, you have to have good comprehension. So you cannot have a model in which comprehension and word production have absolutely no relationship with one another. Similarly, for example, for syntactic production, I just argued you need working memory. So you have to represent the interdependencies between your independent variables also in this model. So what we basically want to do is this very ambitious thing of coming up with a model that has all of these variables in it simultaneously and also represents the interdependencies between our independent variables. And you can immediately see that none of the routine statistical approaches that we have, like ANOVA or t-test or simple regression, can do anything of the kind. But there is an approach that allows you to do exactly this, and this is called the structural equation modeling. And I will be talking about a variant of this, which is called path modeling. So path modeling is basically just the least square approach to structural equation modeling. And there are some important concepts in this framework that I'm going to briefly introduce, one of which is the concept of a latent variable. So a latent variable is, in this case, a psychological construct that we know is real. We are interested in it, for example, comprehension, but we cannot directly measure it. I mean, I cannot, there's no way for me to measure your comprehension. The best I can do is to administer tests that I think best estimate how well your comprehension works. And the model basically allows us to specify these latent variables, which are the variables that we're really interested in, and look at their influence on the dependent variable, which itself is a latent variable. But how do we estimate these latent variables? By the use of what is called a manifest variable. So a manifest variable now is exactly what we can observe empirically, which means it's scores on our tests. So why is it good to have a model that has these two tiers? Why is it good to separate latent variables from manifest variables? Well, a good justification for this is because our tests are never perfect. For example, take word production. So I'm interested in the ability to produce words, and I'm going to administer Western aphasia battery naming test. Well, that's good, but we all know that word production is more than just naming objects. Maybe naming actions also matter. So then what is captured by one test is not captured by another test. but both matter. So I do want to put both of these scores, I want to take them into account when I'm estimating an ability such as word production. If I put all of this in the same tier, like in a normal regression, I'm going to run into statistical problems such as multicollinearity, because these variables are going to be highly correlated with one another. And putting them all in the same tier creates huge problems for actually estimating regression coefficients. But having them in two tiers allows us to extract the common variance from these tests that actually matter for our purpose and bump it onto the latent variable, which is what we're really interested in. So the model really is a very powerful tool for allowing us to put all the kinds of interdependencies that we want into our latent variables and to use a large number of scores in order to best estimate these latent variables and then look at their influence on our dependent variable. So the model, as I'm showing it to you, is exactly the kind of model that we have implemented to look at fluency. The software that I use for this is R, but there are other software that you could use in order to build a structural equation model. So again, remember that what we're interested in is called the inner model, which is the relationship between the latent variables, but we need this outer model to look at some of these effects. So the catch with this model is that, as you can see, it's a huge model, so we need a huge data set in order to be able to estimate the parameters. And the data set that we used for this is coming from Aphasia Bank. Most of the audience here, I'm assuming, are familiar with this Aphasia Bank. It's an amazing database that Brian McWhinney and his colleagues have put together, which has a very, very large number of data points from individuals with aphasia from different centers, all of whom have been tested on the same battery and have been scored with the same guidelines. So for the purpose of the current study, we have looked at 113 of these individuals for whom all of the tests that we required were available. The downside of using the Aphasia Bank is that the tests might not be ideal for the purpose that you want to use them. For example, if I were to build a database for the purpose of testing the fluency model, I would have used different measures of working memory and monitoring and even comprehension. But this is a very nice starting point, because if I have to collect all the data myself for 113 patients, I will not have this model in this lifetime. So I am very grateful for Aphasia Bank for at least letting us have a starting point. A very important point that I have to acknowledge from the beginning is that we are not talking about motor problems in this context, problems such as apraxia of speech, and not because I don't believe that they matter for fluency. Quite the opposite. I believe that they matter tremendously for fluency. But the reason that we were forced to leave out these measures is because the Aphasia Bank didn't have the best measures for apraxia of speech, and most importantly, the measure was missing for a lot of patients that we wanted to include in this framework. And so I'm acknowledging that up front, that the scope of this model is just the cognitive variables that go into sentence production, but it's very important to keep in mind that motor variables matter tremendously for fluency. So now that I have this model, I can go and start looking at what actually does matter for fluency. But before I go ahead and test the inner model, I have to first make sure that I have a good model. And this is another positive aspect of doing structural equation modeling, because it's kind of an interactive model. It allows you to both test a hypothesis, but in the way you can actually look and see if the structure of the model that you have specified makes sense, if the variables you have chosen actually represent what you want them to represent, and what kind of changes you can make to make your model better. So I'm going to quickly introduce some of the checks for you to see how you can refine and revise this model. The first question you want to ask is whether these latent variables that I have specified are actually coherent constructs. So this is represented by something called composite reliability, and it's these numbers that I have put in these circles. Good composite reliability is usually a number that's greater than 0.7. And so that has to do with how well your manifest variables actually represent your latent variable. This is important because sometimes we think that we have a test that really captures the essence of a latent variable, and we think, oh, with these 3 tests that we have totally do the same thing. And when you put them in the context of the model, you see that the composite reliability of your latent variable turns out to be pretty low. And so that's when you have to go and see what is wrong with the manifest variables that you have specified. In this case, we have good numbers, but nevertheless, I'm going to show you how you would go about looking and double checking that. And that's by looking at the values on these arrows that are called factor loadings. So factor loadings basically say that how well your latent variable explains the variance in your manifest variables. So if I have good comprehension, first of all, I expect it to explain both of my comprehension variables well, and I expect both of them to be in the same direction. So poor comprehension should lead to poorer performance on both WOP, auditory word recognition, and on the yes and no task. If I have variables that have different signs on here, then that means that my latent variable is not explaining these 2 manifest variables in the same way. So ideally what you want is high factor loadings on all of these manifest variables with the same sign. And again, high is usually defined at 0.6 or 0.7 and higher. So in general, it seems that most of the variables that I have good high factor loadings. Look here at fluency. So for fluency, the 2 manifest variables that I have specified are words per minute and WOP fluency scores. I have specifically put these 2 into the model because, as I said earlier in the talk, they capture 2 aspects of fluency. Words per minute is good because it's an objective measure, but quantity of speech doesn't seem to be all that matters for measuring fluency. On the other hand, WOP fluency scores seem to be a good proxy for what people actually perceive as non-fluent, but it's not that objective. So I have put both of them in this model so that they can both contribute to the variance. But as you can see, the factor loading for the words per minute is lower than WOP fluency, and this is something that I'm going to come back to later in the talk. My goal is not to go over all the variables that we have specified for this model. I'm just going to remind you that we acknowledge that these variables are not ideal. This was what we had in the aphasia bank to work with. So quickly going over some general definitions. Comprehension is obviously measured with both word comprehension and yes, no tested WOP, which is sentence comprehension. For word production, we had Western aphasia battery naming, Boston naming task, the short version, and also VNT, which is action naming. Syntactic production, you see a number of measures. These have been coded and derived in Yasmin Farouki Shah's lab from the Cinderella story. So each patient's utterance was taken from the Cinderella story and coded with regard to these variables, and I can explain some of them if there are questions about them. Working memory was measured using a number of different measures in the aphasia bank, all of which are variants of the span task. So the span task is when you give the person a list of words or items, and the list keeps growing, and you will measure how many of the items in the list they can actually keep in mind. The problem with the aphasia bank working memory tests is that they all require the patient to actually repeat the words. And you can imagine that in a person with aphasia, this could be a problem because they have trouble speaking. So this was the reason that we actually had to specify links between the comprehension and word production measures also to the working memory task, because if you have poor production abilities, even if you have good working memory, you will have trouble getting the words out. Finally, you can see here that I changed monitoring to restarts because we didn't have good measures to really measure monitoring the way that it should be measured, namely by looking at how well patients detect and correct their errors over a large number of trials. The ideal way of doing this is to have picture naming tasks that are very long and transcriptions of all of this. We didn't have that. So the best measures that we could come up with was restarts and repetitions, again, from the Cinderella story. This is when the patient produces something, but then traces back to the beginning or halfway through the utterance and either changes that or repeats the same segment and continues. This only represents a small part of monitoring, and I'm acknowledging that we did not have better measures to really measure monitoring abilities. But so far, it seems that with the structure that we have good coherent latent variables and manifest variables that at least consistently represent these latent variables. So now we can move on to the next step of evaluation, which is looking at loading and cross-loading of these factors. This is a pretty neat feature of this model, which allows you to see if a manifest variable that you have specified best represents the latent variable that you think it should specify, or it might fit better under a different latent variable. So to walk you through this seemingly complex matrix, keep in mind that the x-axis has all your latent variables. So it's comprehension, word production, working memory, restart, syntax, and fluency. The y-axis represents the manifest variables. For example, I had 2 in comprehension that I think should represent a given latent variable. The first box, for example, shows whether the 2 tests that I had for comprehension really represent the latent variable comprehension. And so if they do, I expect their factor loading on comprehension to be highest and higher than every other latent variable that is listed in the same row. And if you look, that seems to be true for comprehension. By the same logic, that should be true for everything in the diagonal of this matrix. So all the factor loadings should be highest for the latent variable that corresponds to the manifest variable that you think it represents. If you think this is trivial, let me give you an example to show why it's not. Take the example of the action naming task, the VNT. I have specified it under the word production latent variable. It's actually the 3rd bar that you see here. But somebody could object that, well, we know that action naming and object naming are not the same thing. And a lot of people who have deficits in grammatical production actually have deficits in producing action names, because retrieving verbs sometimes, I mean, it could come with retrieving a whole argument structure. And so there are syntactic factors that could go into verb retrieval. So somebody could argue that I should have put VNT under the syntactic production and not the word production. And so the model allows you to test this. If that were the case, then this 3rd bar should have been higher, should have had a higher factor loading on syntax than it does on word production. And we see that that's not the case here. So it reassures me that the choice of putting VNT to represent word production instead of syntactic production was a sound choice. And so in this way, you can really evaluate your model, revise your model, and then arrive at a model that you're convinced is best representative of what's going on in your data before you even look at the results. So now that we think that everything is going well, we can start looking at what we're really interested in, which is the relationship between these independent latent variables on fluency. First, you want to ask, just like any normal regression model, how much of the variance in my dependent variable does the model explain? And this is a R-squared, just like you would interpret any other R-squared, you would interpret this the same way. It's 0.44, which means that 44% of variance is accounted for by my latent variables. And this is actually pretty impressive given the fact that we have left out all the motor problems and apraxia of speech and everything having to do with motor production. And the fact that also we did not have ideal scores for a lot of these variables. And still we can explain about 45% of the variance. So that's good. And now we can look at what is called the path coefficients. So those are these numbers outside of the parentheses that basically specify how strongly each one of these independent variables influence my dependent variable fluency. In the parentheses are corresponding t-scores for these path coefficients. And basically, the way that you can evaluate the statistical significance of this model is by bootstrapping. You can run 1,000 iterations of bootstrapping. The good thing about that is that it doesn't make any assumptions about the nature of the distributions, and you don't have to worry about violations of normality or anything. And so after you do that, you get confidence intervals that either contain or do not contain 0. And so we are interested in those that do not contain 0, which means that the results would be significant. When you look at that, there are 5 of these connections that come out as significant. You can see that all the interdependencies that we specified for our model were in fact significant. Comprehension does affect word production. Working memory does affect syntactic production. And because of the way that we measured working memory, word production and comprehension both matter for that measurement. Interestingly, of the independent variables that we were originally interested in, the only one that seems to directly predict fluency is syntactic production abilities. And so you can now see that we have a dilemma, because it seems that, well, the only statistically significant effect that I have between my independent variables of interest and my dependent variable is syntactic production. But then I have other variables such as working memory that seem to have a statistically significant effect on predicting syntactic production abilities. So now what do I say about working memory? Does it matter for fluency or does it not? Because it doesn't seem to directly predict anything about fluency, but it definitely predicts something about syntactic production abilities, which in turn seems to matter tremendously for predicting fluency. So what do we conclude? Here's another great thing about structural equation modeling, which is the fact that it allows you to look at 2 different kinds of effects. What I'm plotting here as in dark purple is called direct effects. So this, you can see already, syntactic production we saw had a direct significant effect on fluency. What I'm plotting in light purple is what's called an indirect effect. So this is when the variable has an indirect effect on your dependent variable of interest. For example, working memory has a small direct effect on fluency, but it has a much larger indirect effect on fluency. And the summation of these 2 effects is what's called the total effect. And again, with bootstrapping, you could actually estimate the statistical significance of the total effects of your variables on your dependent variable. And when you do that, you see that indeed comprehension, word production, and working memory all have a statistically significant total effect on fluency. So this is neat. What we can conclude so far is that there is a direct and strong relationship between the degree of syntactic impairment and the magnitude of non-fluency. This is great because this is the intuition that all of us had about the correspondence between agrammatism and non-fluent aphasia, but we had such a hard time finding conclusive evidence for in the literature. So now with this approach, we can see that this dependency is real. But there is also indirect influence of several other variables, in our case comprehension, single word production, working memory, that seem to matter for predicting the level of fluency. And this is important both for building a theoretical framework for fluency, showing that indeed all the operations that go into a psycholinguistic model of sentence production matter for fluency, and their impairment can manifest as a non-fluency disorder. And it also matters for therapy, because we now know that, well, this thing can come from all sorts of origins, and in order to take care of it, we might have to take care of different problems in different patients. But now I want to go back and see still, why did we see the strongest and most direct effect coming from syntactic production abilities and not from these other abilities? And there are two potential explanations for this. One is trivial, and it has to do with how we specified the model. So if you remember, one of the two variables that we specified to represent the latent variable fluency was Western aphasia battery ratings. And as I've shown you at the beginning of the talk, these ratings are indeed influenced by grammatical production abilities. So you can then tell me, well, Bonnie, this is silly. You have put a variable in the model that you know is influenced by grammatical production, and then you're showing that grammatical abilities are the best predictor of this variable, which is represented by grammatical production abilities. So that's circular and that's silly. In order to take care of this problem, we built pretty much the exact same model, and this time we took out the WOB fluency scores, leaving only the words per minute measure in there. And now remember that the words per minute measure is completely insensitive to grammatical abilities. There is nothing in that measure that in any way, shape, or form represents grammatical abilities. So now, if the problem really was a problem in specifying the variables, now that we have changed the dependent variable in the model to just be a measure that has nothing to do with grammatical abilities, we should see the influence of syntactic production ability on fluency to go away. In fact, we see quite the opposite. We see that in this model, there is an even stronger effect of syntactic abilities on predicting fluency measured by words per minute. So this allows me to at least refute the trivial explanation and to get to a more interesting explanation, which is, I mean, this is a hypothesis, but I think the reason that you see such a strong relationship between syntactic production and fluency abilities is because they both require cognitive flexibility to output words in the right sequence. And this requires inhibiting the past, activating the present, and preparing for the future. In other words, you have to quickly switch between a number of cognitive operations in order to both maintain the fluency of speech and also to produce a grammatically correct sentence. So in the last 5 minutes of the talk, I'm going to just quickly present some preliminary evidence for the hypothesis that cognitive flexibility, or the ability to switch between tasks, might matter for fluency. This is a work that I did many years ago with Myrna Schwartz. And what we basically did was to choose two patients with non-fluent aphasia, one of whom had inferior frontal lesion, one of whom had a middle frontal lesion. There is no time for me to get to why we chose these two lesion sites, but you can ask me after I'm done. And a control patient who had a lesion similar in size to these two patients, but the location of the lesion was posterior. And these patients were matched on a number of variables. They were matched in age, years of education. They had comparable abilities in single word production. So their Philadelphia picture naming scores were very close to one another. Their auditory word repetition abilities were also comparable, and they all had good comprehension abilities. However, when you looked at their fluency scores, these two patients were non-fluent and the control patient was completely fluent. And this was verified with both subjective WOP scores and also with the words per minute scores. We put them in through a task switching study. And so this is a pretty much canonical task switching study. there are two tasks. One is to label objects as natural or man-made, and the second task is to label objects as small or large. On each trial, the patient sees an object, like a chair. They both see and hear a prompt, for example, natural or man-made, and they have to make a response. The next trial can either be the same kind of trial, which would be called a repeat trial, or it could be a different kind of trial. The task now could switch to small or large, and that would be called a switch trial. And so what we are interested in is what is called the transient cost. So that's the difference in reaction times in a switch trial, like the one I'm showing you here, minus the reaction times in a repeat trial, divided by the mean reaction time for a repeat trial. And so this cost basically determines how well can patients switch between two tasks. The larger the cost, the more difficulty they have in switching between tasks. What I'm showing you here is that transient cost for errors and for reaction times using the button press version of the task. So there was no speaking here. I'm actually not showing you the data for speaking because it was a lot more complex and patients had trouble with speaking, but I can talk about that if somebody's interested. The button press results were very straightforward. The red and yellow are the two non-fluent patients. The purple is the fluent patient, and the blue is a control group of 20 individuals. In terms of errors, everybody's within range, showing that patients could actually do this task, understood the instructions well, and they could complete the task. When you look at the reaction times, on the other hand, both non-fluent patients had transient costs that were statistically significantly larger than that of controls, and the fluent patient, on the other hand, had costs within the range of controls. So we found exaggerated transient costs in the non-fluent individuals, but not in the fluent individual who was yoked to them in all aspects of production, including the ability to produce single words. So to conclude, I think the problems in comprehension, single word production, and working memory can all contribute to non-fluency, but syntactic production has the closest link to fluency because they tap into a lot of similar underlying processes, including executive control abilities. So some shortcomings to be acknowledged is that, again, this model was a first step. It was by no means complete, and that is reflected in the fact that we can explain less than 50% of the variance of fluency, and a more comprehensive model has to include other variables such as apraxia of speech and executive control abilities. Another thing that I would definitely do is to specify better measures, better manifest variables to represent our latent variables such as working memory and monitoring. So one of the reasons that we didn't see a contribution of monitoring to fluency is most likely because we did not have the ideal measures to represent monitoring. And ultimately, one of the goals of this modeling project was to show you that all of these variables can themselves be broken down into smaller models. For example, I'm talking about syntactic production abilities, but obviously syntactic production is not a unified construct. There could be different aspects of syntactic production that could be selectively impaired, and some of these aspects might have a stronger influence on fluency than some other aspects. So you could very well make mini models of each of these independent variables and give them their own structural equation model. So with that, all of what I have talked about is you can find it in this paper that Yasmin Farooqi-Shah and I published last year, and it also includes a tutorial on how to go about checking the different aspects of a structural equation model. And finally, if you run into any trouble with constructing these models and running the code, by all means, send me an email and I'm happy to help you out. With that, I want to thank my good friend and colleague Yasmin for all the help that she gave me in putting the measured different manifest variables into this model. Brian McWhinney and his team for building the aphasia bank, and everybody who has contributed to this bank. Many universities have participated. The NSF grant that funds my work, and all the individuals who have an interest in sharing their data on aphasia and who like working on the problem of nonfluency. Thank you so much.
Thank you very much, Bonnie. I don't know if you can see if you get questions on the chat box. If you can't, I can read them out to you. There's no questions yet. I want to start with questions from our end, if that's okay.
Yes, please.
Hi, Bonnie. I'm Bertie. I'm one of Julius's postdocs. So when we do regression, we always do leave one out or something like that, so we don't overfit models, and so you can figure out if your model were to fit someone you didn't include in the data. So can you do that with structural equation modeling, or is there a way to kind of take that into account?
In theory, you should be able to do this. Usually, because the data that you need for structural equation modeling is so much that you pretty much don't want to leave some of it out. But in theory, you should be able to do this, because what you get is regression coefficients, just like any other regression model. So in theory, you could then build a model to see if the model can estimate something about unknown cases. But because the architecture of the model is pretty complex, I have not seen that as a routine approach to structural equation modeling.
I was wondering, Bonnie, looking at the model itself, so it seems that it's pretty clear that the starting architecture of the model has a big influence on the parameter values that you're going to find, right? And I was just wondering what your reason was for not drawing a line, if you will, from word production to syntactic production, because syntactic production can also be affected by either directly or indirectly by word finding problems, for example.
Right, you're absolutely right.
And if you do that, whether that changes the rest of the outcome.
Right. So this is one of the cases where I said it's a really good feature of this kind of model, because you can interactively test what is the right architecture for the model. And I remember when we did this, we first started off by a model that had a lot more links, and then you can test and see whether at the end there is a significant effect on that variable to the other variable that you have specified. And if not, you can then drop that connection. And so this is one of the things that we did. And it seemed that word production did not have a direct effect on syntactic production. And part of it might be really because of the way that we specified our syntactic variables to be as removed from word production abilities as possible, so we could represent them with two different variables. But yes, this is one of the things that we actually tried. And because it wasn't significant, we dropped it from the model, at least in this data set.
I had another question. If we know that part of what is termed here non-fluency can be accounted for, or at least is predicted by measures of syntactic production, that's still based on a big group analysis of 100+ participants, right? And so going back to individual patients, given your results, do you think fluency is a valuable or a valid construct to talk about when we talk about aphasic patients? Because it's pretty clear that there are all sorts of aspects of fluency that are perhaps not predicted by syntactic production. So there are also other types of non-fluency, right? Not just the motor stuff that you addressed as a caveat, but even, obviously lexical production problems can also lead to non-fluency, even if your data say they don't.
This is a great question. And when Yasmin and I were talking about this was a question that I asked myself and her a couple of times, and said, hey, should we completely just do away with the concept of non-fluency? And because it seems to be so complex and it doesn't really tell us anything. But then there are some reasons that I think it's still useful to use this construct. And part of it is because we have asked a lot of our patients what about their speech bugs them the most. And invariably what we get is the answer that I'm not fluent. And so for them, it seems to be a coherent construct. You know, the patient doesn't care and doesn't know what exactly is the mechanistic explanation behind this, but they want to convey to you in one word, what is it that bugs them the most? And for most patients, it's the fact that they're not fluent anymore. Another reason is that for clinicians, I mean, we've had this debate a lot with clinicians of at least, you know, dropping some of these characterizations such as Broca's versus Wernicke's, and we haven't been able to even make any headway there. But with fluency, again, clinicians have the tendency of dividing patients into fluent and non-fluent. So we can't get rid of that definition, even if we wanted to. So we might as well keep it, but try to define it and try to kind of convey the message that what we are looking at as one problem is actually a syndrome, and the syndrome could have multiple causes. So if I have to answer, I would say let's keep the concept of non-fluency, but keep in mind that it's not a homogeneous construct.
Yeah. We have an online question. I don't know if you can see it yourself in the chat box.
Can you tell us why you chose the two patients, one with the inferior frontal? Okay, yes, I can. So the question is, in the last part of the talk, when I showed you the two patients for the task switching study, I said one of them has inferior frontal lesions, one of them has middle frontal lesions, and I said there's a reason for this. So now I'm getting the question what that reason was. So we first ran a large VLSM analysis on a very large number of patients from the MOS database. We had, I believe, 106 patients in that database. And we ran this a little differently than other people do it. We first partial out of single word production abilities from WOP fluency scores. And the reason we did that was that we didn't want their single word production abilities to really come into effect with regard to their fluency, because obviously if you can't produce single words, you cannot produce running speech. So we didn't want that to affect it. So we first built a model with WOP fluency scores as a dependent variable, picture naming as the independent variable, and took the residuals of that model and looked at a VLSM result of the correspondence between lesion sites and those residuals. Two of the major sites that we got for this were the middle frontal gyrus and the inferior frontal gyrus, and a lot of underlying white matter. So we then got curious about, oh, this is interesting. Is there any difference between these two sites? In other words, do patients who have damage to the inferior frontal gyrus show a different pattern of non-fluency than patients with middle frontal gyrus? So that's why we chose those two patients. Then we looked at their QPA to see if there was any difference in syntactic production, and we didn't find anything there. However, we ran the same study that I just showed you, but with the oral responses. And now we got very interesting results. We found out that both patients had trouble in switching, but they had troubles switching at different levels. The patient with the inferior frontal lesion constantly confused the two words within the same task. For example, you show them the picture of an apple, she would say large instead of small when the task was small versus large. But she did not get confused between the two tasks. So if the task was small and large, she would not say natural in response. On the other hand, the person with the middle frontal gyrus lesion could not keep the tasks apart, but was not confused about the two responses within the same task. So you would show her an apple and the task was small or large, she might respond natural, but she would never say large for the apple. So we did find out that these two, the lesion to these two regions actually did matter for switching, but at different levels, at the level of response versus the level of the task. It's good. I got it. I'm wondering if you have any thoughts or done any of these task switching paradigms with patients with stereotypical recurring utterances. Would you see the type of non-fluency as a sort of extreme case of not being able to switch from one word? No, I mean, this study that I showed you is the only study that I have done on task switching, and I've done it when I was a postdoc many years ago, and then I moved on to different things and never actually repeated it. But now when I put this talk together, I was reminded of how cool this is, and now I'm thinking I should go back and do more of this. So it's definitely something that we want to look at, but these two patients are actually the only two patients I have ever run in this task, and neither of them had a lot of stereotypical speech. But I'll get back to you. I'll do it and get back to you, I promise.
So my other question was, I was really interested to hear your account of the potential relation between syntactic production and fluency, because you don't say one causes the other, as would be I think the first pass for most researchers, but you say no, they have a common cause.
I think so.
So how strongly can you tease those apart? Because it would make perfect sense, right, that a syntactic production problem in itself can lead to non-fluency. If you have trouble building sentences, then that leads to sentence construction problems that, it's not too crazy to think of that in terms of non-fluency, or for that to lead to fewer words per minute, etc. So
right.
How much of this is a belief, and how can you tease them apart? Really, I know you did the experiment with the executive function, but that can still mean that the executive function can cause a syntactic problem, which in turn causes the non-fluency, right?
Right, and I'd be perfectly fine with that explanation. So what I was trying to point out is that grammatical difficulty problems are not problems in necessarily the deficit in the knowledge of grammar. So that's, I think, the point that I want to make. So you could have a grammatical deficit problem in which the patient has lost the grammatical knowledge, so they don't know what needs to go where, as opposed to having an operational problem, which is that the grammatical knowledge is intact, but you don't have some, say, non-linguistic abilities to basically enforce that knowledge. And that is the position that I'm taking, is that the reason that you have grammatical deficit problems is because you have executive control deficit problems, even though you may have completely intact syntactic knowledge. And then I'm fine with the position that, okay, it might be the same problem in you putting the words together in a grammatical context that then leads to you looking non-fluent. But the point is that it's not grammatical problem as a problem in grammatical knowledge that leads to fluency. Does that make sense?
It does, but there's as a separate issue, right? There's nothing in your data that makes that point, right? There's nothing in your past equation modeling that makes that particular point.
Oh, yeah, no. In the equation modeling, there is nothing even about the origin of the syntactic deficit, which is why I said one good avenue for furthering this is to go and just look where syntactic problems themselves come from. You could make a structural equation model with the syntactic deficit as a dependent variable, and then see what kind of abilities even predict the syntactic problem. And so cool. the last experiment that I showed you was just one hypothesis about what could lead to grammatical difficulty problems, which I think is executive control, but it's in no way conclusive, and we just have two patients and we haven't looked at other variables. So this is at this point just a hypothesis.
Great. I don't think we have other questions. We have no questions online. So thank you very much, Bonnie. It was great.
Thank you so much. Take care.